Now we are going to pass to the Planche-Rare theorem, okay, so the initial statement is that Planche-Rare theorem, the Fourier transform maps the intersection of L2 of G and L1 of G isometrically onto a dense subset of L2 of the dual group. Okay, so surely, since we have this operator acting isometrically on this subset, and this subset is dense in L2 of G, an immediate consequence is that the Fourier transform extends uniquely to a unitary operator of L2 of G onto L2 of gamma. So this is probably more well-known statement, but of course we first prove this, and if you remember, in the case of Rn we do the same, but the only thing that probably it's reasonable to start with the Schwarz class functions or something like that, with infinitely differentiable functions that are rapidly decreasing at infinity together with all derivatives. And here again, there is nothing like that, and we start directly with this intersection. So okay, the proof goes very. So now the proof is short even, because we know the inversion formula, the Bochner theorem, and so on. So take a function f in this intersection. And as before, take the convolution of f and f tilde. I remind you that f tilde of x is f of minus x bar. Then this function is positive definite. It's positive definite, and what do we have? What else do we have? Sure, it is in L1 because f is in L1, so f tilde is in L1, so this one is in L1, and moreover, the Fourier transform which is equal to the absolute value of f hat square. This we already calculated many times. So if you take the Fourier transform of this function, then we obtain the product of the Fourier transforms of these two functions, and if we take the Fourier transform of f bar, of f tilde, we obtain f hat bar. So we have this, and now by the inversion formula, g of x is equal to the integral over gamma of x, this guy. Well, we have this equality, and I remind you that in this case, even this function is continuous. So this is true everywhere. So we put here x equal to 0. So it follows that g of 0 is equal to integral over gamma of f hat of gamma squared d gamma. And what is that? And this is, let's write it down. G of x is equal to the integral over g of f of u, f bar of x minus u. So du, so g of 0 is equal to the integral over g f of u, f f tilde. And f tilde, what is f tilde? F tilde is, so I put here x equal to 0, then I put minus, and I take bar. So and we see that this Fourier transform is an isometry on this set. And what remains is to prove that the image is dense. The image is dense, and for that, let us denote this space by something. Let phi be this space, and what is clear that phi is stable under multiplication, by characters, and also translation invariant. So the space is stable under multiplication by characters. It's clear, absolutely clear, and also it is translation invariant because these two spaces are translation invariant. Now it follows that if I take the Fourier transforms of functions of this sort, then the space is also stable under multiplication by characters and translation invariant, because this stability implies invariance under translations of the Fourier transforms, and vice versa. This second statement implies that it's stable under multiplication by characters. And now I must show that this is dense in L2 of gamma. So we want to prove this. And for that, if it is not dense, then it can be separated. There is a non-trivial linear functional, which is 0 of the space. So suppose that psi in L2 of gamma is a function such that it is orthogonal to all functions phi for all phi in this set of Fourier transforms. Okay, so I must prove that this psi is equal to 0. And we use the fact that this is invariant under multiplication by characters. So from this we can deduce that also the following integral is equal to 0. Simply from the translation invariance of this space, it follows that we can multiply here by this function. So this is equal to 0 for all x. Here this function is in L2 of gamma, this function is also in L2 of gamma, so their product is in L1 of gamma. And we see that such integrals, what we call the inverse Fourier transform of this product, this L1 function is equal to 0 for all x. And so we use the uniqueness theorem for the dual group. We still don't know the uniqueness theorem for the initial group, but for the dual we know it, so we use it. And it follows that psi bar is equal to 0 almost everywhere. Is equal to 0 as an element of L1, so almost everywhere. And suppose now that psi is not equal to 0. Then what follows from this? So we have this relation, and we use now the fact that this set is translation invariant. So if psi is not equal to 0, then psi is not equal to 0 on some set of positive measure. And if and surely this set phi hat has non-zero elements. So we can find phi which is not equal to 0 somewhere, and then we can shift it to the point where this guy is not equal to 0. And then there will be a contradiction. So a contradiction. By translation invariance. Okay. So we have proved that really the Fourier transform is a unitary operator, mapping L2 of G onto L2 of gamma, and from this surely it follows that we have the Parseval inequality let's use this symbol f hat also for all f in L2 of G. Simply we understand is as a result of the limit procedure, this hat Fourier transform is defined literally on this set, but then we extend the separation by continuity to the entire L2 space, and we still use the same symbol, but we should remember that it is not genuine Fourier transform, so so-called L2 Fourier transform, and from the fact that the Fourier transform is a unitary operator, it follows that it also preserves scalar products, that is the integral of f. So this is what is called the Parseval identity. And now we also can deduce some useful corollary of the theorem. It will not be used immediately, but still it is interesting and useful. So corollary A of gamma. Do you remember what A of gamma is? This is precisely the Fourier transforms of all L1 functions. So A of gamma is equal to the collection of functions of this sort, where F1 and F2 belong to L2 of the dual group. So this is precisely the set of all convolutions of L2 functions. We know that this is continuous. Convolution of any two functions is continuous, and so there was even a stronger statement that if we convolve a function from LP and LP prime, then we obtain a continuous function. And here two and two primes are the same. So this is continuous a priori. But in fact, this convolution belongs to A of gamma. Okay. What is A gamma? A gamma is so yes, I asked this. A gamma is precisely L1 of G hat. So this is the Gelfand algebra of L1, the set of Gelfand transforms for L1, the set of Fourier transforms for L1, and so on. This is simply a consequence of the fact that every L1 function is a convolution, is a product of two L2 functions by a Fourier transform. So here we start with the Parseval identity, and let's replace here G bar to G. What will happen? So we obtain the integral of fg is equal to the integral of f hat of dx gamma, and here we shall obtain something like that. Okay? So I've started to prove this statement, and for this I use this Parseval identity. In this form, I don't want to have complex conjugation here. Then, again, we already in this identity, we replace G, we substitute this function, gamma 0 of x bar G of x for G. So replace G by this function, and then we arrive at the following formula. This is the left-hand side, and on the right we simply obtain, when we take the Fourier transform of this function, we simply obtain the Fourier transform, shifted Fourier transform. Like this. Okay? And this is precisely f hat of f hat star g hat of gamma 0 by definition. Okay? So this relation which follows from the Parseval identity shows that also on L2, not only on L1 but also on L2, we have the following natural formula fg hat of gamma 0, which is here, is equal to f hat star g hat of gamma 0, and the novelty is that here we may assume that this function sin L2, and we deal with the Fourier transform in the sense of L2. Now, it suffices to note that a function h is an L1 of G if and only if h is equal to fg, where fg belongs to L2 of G. And so from this relation we obtain this one. Well, as I thought, this will be used immediately. Simply, it is nice and interesting. But what will be used immediately? Probably this is not so nice, though simple and short. But what I'm going to prove today is the Pendragon duality theorem, and to prove it, I will need in particular a sort of not uniqueness, but a sort of technical statement. So another corollary of Planck-Chevreul theorem. Another corollary. Suppose E is a non-empty open subset of gamma. Then there exists a function f in A of gamma, f in A of gamma, I write this way to indicate that in fact LF is an L1 of G. So to write F hat is in A of gamma is the same as to state that F is in L1 of G. Well, so that F hat is not identically 0, but F is equal to 0 outside E. So again, take an open subset of the dual group gamma, then somehow we can separate points in this subset from the complement. But the point is, the important thing is that we can separate them with Fourier transforms of L1 functions, which is not quite clear a priori. Why? So this algebra is something strange, narrow, and why are we able to produce such a function which separates point in U? Still, this is possible, and well, this follows from this fact, for example, but probably there are other ways to do this. Okay, so Haar measure is regular, so I start to prove. Take compact K in E so that its Haar measure is positive, and take a compact neighborhood of 0 such that K plus V is included in E. So this is possible by compactness. You understand, we already did such things. Let me repeat the argument. So for every point in K, we can find such a sequence, such a neighborhood V. So for every X in K, there is a compact neighborhood of 0 Vx, so that X plus Vx is an E. This is because E is open. Now these sets form a covering, an open covering of K. Then a finite number of these sets covers K, and then we simply intersect all Vx in this finite covering to obtain this V.
In the corollary, should be F hat to 0 outside E.
Where?
The middle background. But F equal to 0
F hat.
Yes.
Sure. Okay. And after we did that, we simply take the inverse Fourier transform of the convolution of the characteristic functions of these two sets, K and just convolve them. We convolve them. Then we obtain a function with these properties. It will be supported on the set E. It will vanish outside E. Well, since these two functions are nil2, this convolution is in A of gamma, and so it is the Fourier transform of such some function L1. So everything follows. Now we pass to what is called Pontryagin duality theorem. So still we have a locally compact abelian group. And gamma, the dual group. That is a group of characters on G. Then it is a locally compact abelian group itself, and it has its own dual that is denoted by gamma hat. Then surely we have the following embedding. So each element of G can be treated as a character on gamma. So to say we have this embedding, to be more precise, let's define a mapping alpha from G to gamma hat. Simply in this way, alpha of x on a character gamma is equal to gamma of x. The usual second dual construction. So the Pontryagin duality theorem says that alpha is a topological group isomorphism of G onto gamma hat. So this means more or less that if we take the dual of gamma, we obtain G again, and there is no anything similar to non-reflexive Banach spaces and so on. So let's start to prove this. So what we know that gamma separates the points of G. And I remind you that this is non-trivial. This is a consequence of the inversion formula. Before inversion formula, we could not prove that. So, that is, this means that if you have two different points of G, then there is a character which takes different values.
This from the...
This is some consequence of the inversion formula. We did this last time.
Yes.
We did this last time, so this consequence is simple but not quite immediate, so some argument is needed. So we did this last time, so this separates points. The fact that this mapping alpha is multiplicative is clear. This remark shows that alpha is an algebraic isomorphism of G onto its image. So this we know. And to finish the proof, we should verify three statements. First, alpha is a topological isomorphism of G onto alpha of G. Second, alpha of G is closed in gamma hat. And third, alpha of G is dense in gamma hat. Well, when we prove the three statements, we shall prove the theorem. Well, the first statement is also something non-trivial, and it is a consequence of the inversion formula. I recall you that after we proved the inversion formula, we showed that these standard basic sets, which we defined some time ago, they form a base of neighborhoods in the group G. So, well, okay. Now, how do we define the topology in well, where it is? Okay, topology in gamma hat. Take a compact set of G of gamma. Then the sets of this form. Gamma hat, little gamma hat, in capital gamma hat, for which the third one are varies, for all, for all gamma in C. So here C varies and R varies. So this sets from a base of neighborhoods of 0 in gamma hat. Okay, so this is simply the definition of the topology. Well, okay, well, not quite the Gelfand topology, but we proved that this is equivalent to the Gelfand topology. So this is the basic definition. Now, what we proved probably last time or probably 2 weeks ago, that if we restrict here to the elements of G, then we obtain a base of neighborhoods in G. So the set of all X in G, for which 1 minus gamma of X So if we only consider the characters in this group of the form alpha of something, then we obtain a base of neighborhoods in G. And this means that this alpha is continuous with its inverse at 0. And since everything is invariant under translation, it is continuous with its inverse at all points. So we have proved the statement A. So alpha is a topological isomorphism. Now we prove this thing B. So let gamma hat. I put hat to indicate, or probably simply gamma 0, be some point in capital gamma hat, so that gamma 0 is in the closure of alpha of G. And we must prove that, in fact, this gamma 0 must belong to alpha of G. Well, I want to tell that since we have proved this topological isomorphism, we know that alpha of G is itself a locally compact abelian group. So it is locally compact abelian group. And well, surely we must use this compactness argument somehow to prove this inclusion, but I want to tell you that we also must use the group structure. For example, consider, say, the real line, well, which is a locally compact space, even a group. And consider, say, the interval -1, 1. Then there is no way to prove that its endpoints belong to it. These endpoints are cluster points of this interval, and this interval is locally compact itself, but well, surely we cannot prove that they belong to it. So we must somehow make use of the group structure, and well, probably the shortest way to explain this is the following. Well, are you familiar with convergence of nets? You are, I think. Yes. So it will be easy. Well, okay. There is a net. X alpha of points in G, so that X alpha, another letter, some S, say. So that alpha of XS tends to gamma 0. Okay. Now we take some compact neighborhood of 0 in alpha of G in this image. I already told that this guy is a locally compact group, so there is a compact neighborhood of 0. And also we know that the topology is induced from gamma hat. Well, so there is a symmetric compact neighborhood W of 0 in this gamma hat, so that W intersected with alpha of G is included in this V. This is because the topology is induced. Now we use this, and it follows that all elements alpha of xs lie in gamma 0 plus v for all s starting with some point. Okay? Even let me write this way. That's also possible. Sure. W minus W. Then alpha of xs minus alpha of xs prime lies in plus W, sorry. Here I must put W last in W minus W, and this is in V. For all s in this prime greater than S0. Okay?
What is S here?
This is some index set which is ordered and directed.
We do not define now.
Not defined. Well, it is a net. So in principle, this may be the set of indices may be the set of all neighborhoods of gamma, something like that. Just take all neighborhoods of gamma, and then in each neighborhood take an element of this sort, and so it is some directed set. And then we have this. Then we have this. Now this belongs to some compact set in the group alpha of G. Alpha of G. So if we fix some S prime and take a cluster point in S, we see that gamma 0 minus alpha x S prime belongs to V, because this is compact. Okay? Well, and this means the gamma 0 belongs to alpha of G, because this is there.
This is cosinet.
Yes, Cauchy-net, yes. You cannot do here without passing to this Cauchy-net, because you should eliminate somehow this point gamma 0 from your considerations. Otherwise, you may be in this position, which I draw. Well, so you eliminate this point gamma 0 by passing to the Cauchy-net, and then this Cauchy-net turns out to be included in some compact subset of the group alpha of G. And after that, you take a cluster point. And, okay. So we have proved this B. Yes? And the last thing to do is to prove C. Well, but we already know that this thing is closed. So I cheat. I am cheating a little bit when I tell dense here, because if it is closed and dense, well, so simply I just prove that alpha of G is equal to gamma hat, because its density is the same as, I know already this is closed. So suppose it is not equal to gamma hat. We know it's closed, so density is the same as equality with gamma hat. Suppose it is not, then the complement of this alpha of G in gamma hat is an open subset of gamma hat. Yes? And we have proved that then there is a function which vanishes here but non-zero here. There is a function f in A of gamma hat in this Gelfand space, Gelfand algebra, so that f is equal to 0 on alpha of G, but f is not identical to 0. So this is the second corollary to the Plancherel theorem. But now this function is in A of gamma hat, so it is the Fourier transform of some function in L1 of gamma. Okay? There is a function phi in L1 of gamma, so that f of gamma hat is equal to the integral of a gamma of phi of gamma hat of gamma. So this is the Fourier transform of something. And now simply put here, calculate here for gamma hat equal to alpha of x, where x is in G. So then we obtain 0 here, yes? Because our function f is 0 in alpha of G. We obtain 0 here, and we are under the conditions of the uniqueness theorem. Well, we have some function in that one of gamma, and well, we see that its Fourier transform is inverse Fourier transform. Is equal to 0 for every x in G. Okay? And this is precisely the uniqueness theorem as a form we proved it. We have a function gamma, and its inverse Fourier transform is equal to 0. Then this means that phi is 0. And since phi is 0, then f is 0, but our f is non-zero. And so we obtain a contradiction, and the Pointare-Agnew theorem is proved. Now, all this allows us to symmetrize many statements which were non-symmetric in our previous discussion. Well, let's simply list them. First, G is compact if and only if gamma is discrete. What do we know? We know that if G is compact, then gamma is discrete, and if G is discrete, then gamma is compact. Because of symmetry, now it becomes symmetrical. Next, now we may state the uniqueness theorem not for gamma but for G. If we have a measure on G, well, I denoted it in this way, and mu hat its Fourier transform is equal to 0 identically, then mu is 0. We know the same for measures of gamma. If you have a measure on gamma, and if it's in inverse Fourier transform function of G is identical to 0, then this measure is 0. Now everything becomes symmetric because of Pointare-Agnew duality theorem. Next, what was claimed many times, if G is not discrete, then the algebra L1 of G has no unity. Really has no unity. It can be proved now. Not because we don't see where the unity may be, but it really has no unity. If G is not discrete, so the proof, if G is not discrete, then gamma is not compact. This space A of gamma consists of functions that tend to 0 at infinity. This is not compact, so this is something non-trivial, and this is included here, and so it cannot contain any non-zero constant. So there is no unity here. Because otherwise there would be unity here, and unity here is for the function 1, so well, also we may state the following supplement to the inversion formula. Well, suppose we have a measure on G, a finite regular barrel measure, and suppose we are so happy that its Fourier transform turned out to be an L1 function. So in principle, this is a continuous, uniformly continuous function. But suppose it is an L1, then mu is absolutely continuous. Is density F, and this F is the inverse Fourier transform of this function mu hat. So even in this form, this is true. Why that is so? Now again, we use the symmetry of the groups G and gamma, and we claim that this function mu hat is contained in what was called B1 of gamma. So this is a Fourier transform of a measure, and at the same time an integrable function. Yes, and so for it the inversion formula, but applied to the group gamma, can be is valid. Yes. So what do we have? We see that if we define a function, so let's define a function f by this formula star. And then by the inversion formula, but this time for the pair gamma G. Again, it is reversed. So what do we have? We see that by the inversion, not formula, rather by the inversion theorem. Entire theorem, not merely the formula. So we see that this function f is an L1 of G, and we can recover this function, this density, this function mu hat from f. But also, what do we have for this Fourier transform? Initially, we have the following formula. And so when we compare these two formulas, we see that the measure f of x dx coincides with mu, again by the uniqueness theorem, but this time applied to G, not to gamma. Mm-hmm. Okay. There is another very general fact about locally compact abelian groups. It is also due to Pantiregin, it seems to me, though there were some people who proved some partial results before, but it seems to me that in this generality this is proved by Pantiregin. And I want to present the proof here. Maybe I will not be able to do this entirely today, but next time we will finish with that. So this is the so-called structure theorem. Let G be a locally compact abelian group. Then there is an integer n such that G contains an open subgroup of the form H direct sum Rn, where H is compact. I think you understand what the direct sum is. Direct sum of two groups. Yes, I think. Okay. Anyway, we shall discuss this a little bit because there are some subtleties here. But so what does this mean? When we have an open subgroup, let me explain. Suppose that G is a group and G1 is an open subgroup. Then let's consider the cosets of this open subgroup. So the sets of type, the classes of type X plus G1, equivalence classes, cosets, cassettes determined by some elements of G. Of course, we have splitting of our group G into these cassettes, in non-intersecting cassettes, and every cassette of this type is open because the shift of our open subgroup. Then all of them are closed. Yes? So G1 itself is also closed. And this means that if I consider the quotient group of G over G1, I obtain something discrete. So if we take the quotient.
Here H is discrete, here H is compact group.
Sorry?
Here H is a compact group.
H is compact group here, yes. So here, let's consider this situation. So the quotient of G over G1 is discrete. So in a way, the structure of this group is fairly simple. The quotient is discrete, so you have some collection of shifts of this G1 over with elements of a discrete set. What is probably not quite pleasant, but true, that it may happen that there is no section here for this quotient map. So I mean that this gamma, it is not always true that this direct sum is isomorphic to G canonically. There are some examples. It may be something more complicated, but still, it is very close to being so, to being something like that. At least in the topological sense, this is easy. So in fact, all non-trivial topological structure is hidden here in G1. And as to this G1, the structure theorem tells us that this time this is direct sum of something compact, about which I don't know what is that, but it is compact, so not so much probably easier to handle than an arbitrary non-compact group, plus Rn. So all non-compactness is hidden here in this Rn and in this discrete quotient. Otherwise we deal with a compact subgroup. Okay?
And gamma R, because it's available, no problem. So it's a group.
Well, okay, so I'll prove that, but probably not today, because there are some words to say before I prove. Now, what should I do also? Well, what's about direct sums? When we have two subgroups or a finite number of subgroups, probably this is something which need not be explained, but when we have an infinite number of groups, then there are at least two ways to define a direct sum. So there is what is called, so consider a family, G alpha, a family. Of locally compact. Well, I put this in brackets because in parentheses because I don't insist on this topology at some statements. Abelian groups. Okay. Then there is what is called the direct sum. It is a collection of all families such that the set of alpha for which only finitely many of x alpha are non-zero. This is what is called the direct sum, and there is another thing, I don't know how to denote this. Somebody denotes this pi and calls product, somebody uses the term complete direct sum. This is the same, but without this restriction. We consider arbitrary collections of elements. Direct product, yes, but well, when you deal with abelian groups, then probably the term product is not quite appropriate emotionally. Still, it is a sum. I don't know. Well. Now, if we have topology in all these groups, then this is endowed with the product topology, and this is a subspace of this thing with the product topology. Oh no, that's otherwise. That's otherwise. At least what should we say that when our groups are all non-compact, then this product is not in general a locally compact group.
It's not what in general?
A locally compact group. It is a group, but not locally compact, even if there is topology. If you take, say, an infinite number of real lines and take their product, then you obtain a space which is not locally compact.
This is locally compact if and only if finite.
Yes. So when you deal with locally compact groups, then this product is normally used when your groups are all compact. Then this product is compact by the Tikhonov theorem. And there are some interesting groups of this sort. For example, this dyadic group. Do you know what the dyadic group is? Dyadic group. So consider the group it is probably it is useful to write it multiplicatively as a group of two elements minus 1, 1, and the operation is multiplication. So this is a discrete group of two elements, and when we consider the countable product of such groups, we obtain what is called the dyadic group, D, and it's very easy to realize that this group D is more or less canonically isomorphic to the counter set by the dyadic expansion of a real number. And, so the counter set is the set of all whose triadic expansion has only signs 0 and 2. Yes. Whose triadic expansion doesn't contain units. So it is just a set of sequences of zeros and twos, and so it is equivalent to this one. What is interesting here is that when all your groups are compact, and you want to consider the dual group of this, so when all of them are compact, this is also compact, yes? Then you obtain the sum of G alpha hat. This will be a discrete group, and this will be the sum. I'll leave it to you as an exercise.
Okay.
So it is clear that all points here are characters here, and you should prove that there are no other characters. If there are some other characters, then there will emerge some divergent product of numbers equal to 1. So in particular, when you consider the dual group of this, you obtain its characters. It is a sum countable system, and if you identify the counter set with the segment 0, 1 in the usual way, you obtain what is called the Walsh basis in L2, Walsh functions. These are products so that okay. And yot of epsilon, epsilon is a point here, is equal to epsilon yot. So when to read this as a segment, this will be the Rademacher functions. And the Walsh functions are arbitrary finite products of Rademacher functions, so they form a basis in L2, and so also a very prominent orthogonal system, which turns out to be a system of characters of some group. A similar pattern arises when we multiply other discrete groups. For example, we can take, say, the group Z3 and take an infinite product of the threes, and they will be what's called triadic group. And okay, so this way. And again, vice versa, if you take a sum of discrete groups and take its dual, you obtain the product, complete product of compact groups.